So should we go ahead or should
Yeah,
we wait?
Yes.
Yeah, go
Well,
ahead.
I think Sam doesn't need a long introduction because most of you know him. Sam used to be here at UNH, as you probably remember,
Mhm.
and now he is at the University of Wisconsin. And yeah, tells me that he has been there for a year now. I couldn't remember that long. But anyway, Sam, it's good to have you here. I am not, you can read his bio. Uh, Yourself. He got his PhD from University of Wisconsin, so he has gone back home to sort of speak.
Ish, yeah, right.
Thank you,
uh,
thank you for. I shouldn't say coming and presenting, but thank you for presenting and welcome.
oh gosh, Mel, thank you so much. It's my pleasure. And I also want to thank Kristen Vanderveen, who extended the invitation to me to contribute to this summer's conference. And so, you know, if we start talking about things that you want to know more about or you want more information, there's my email and Twitter handle. My need for social media validation is especially heightened in pandemic times, and so do with that as you will. And so when I thought about what I could contribute to NEAC this summer, I did a lot of reflection on sort of where my current interests lie, which is a lot with faculty professional development and student learning. And I thought a nice way to sort of bridge the audiences of this particular conference is to talk about how I see a document which I believe most people here are familiar with, which is a framework for K-12 science education, and how that is actually influencing and affecting work in the higher education space. And so for those who aren't familiar, I should just ask everybody, are you familiar with the framework and GSS, or
Yes.
should I explain a little bit?
Now, it was the topic of one of our entire conferences at Mel's school a couple of years ago.
I think
Okay.
Sam presented at that time. I think, didn't you come
Yeah,
to
I think 10
Pittsburgh?
years ago. So I'll just blow past through all of this because you are very familiar that the framework centers around sort of a three-dimensional model. And I guess an important piece that I'll come back to later, especially with regard to disciplinary core ideas, is the idea that I view our role in education as teachers to help students really construct their knowledge and go from a more novice type of picture of knowledge, which is represented there on the left as a very fragmented but nonetheless dynamic collection of facts, to a more expert way of that knowledge organization, which is organized and contextualized and a lot more easily operationalized in various contexts. And that's the idea behind a disciplinary core idea, that although they're sort of discussed in ways that are more like, well, this is what experts know, this is what it's facts, that's a little bit undercutting their purpose. And this will come back to a lot of things I'll talk about today, in that they really are tools for understanding more complex ideas or explaining phenomenon. And they definitely mirror how experts think about their disciplines. Practices, I think we're all pretty good with, and there they all are. And then I'll just say a little bit also about cross-cutting concepts, because I think that these are the most misunderstood of the three dimensions of the framework. They don't necessarily, they aren't really as packaged as the core ideas and the practices are, as being recognized as important in what scientists do and how experts use their knowledge. But taking off on work from Rivet in a paper a couple of years ago, the cross-cutting concepts serve a couple of different purposes, actually, depending on their context. First and foremost, we can think about them as sort of tools or lenses. They provide, and here they all are, sort of complementary approaches to thinking about scientific phenomenon. And so you can sort of view a phenomenon, perhaps something like the decrease of atomic radii when you go across the periodic table, you could think about that as a pattern. You could think about the energy relationships that sort of underlie that particular phenomenon. You could think about models of why that happens, and how the nuclear charge model, for example, gives rise to a cause and effect relationship with those data. And so these cross-cutting concepts are in ways tools or lenses to look at phenomenon. Another way that Rivet sort of expounds the cross-cutting concepts are as epistemic heuristics. And what I mean by that is essentially rules of the game, right? They are ways to help students understand that there are often implicit scientific norms and ways that we go about thinking about constructing and interrogating scientific phenomena. And so they are perhaps making these scientific norms explicit to our students. And then finally, we can think of them as bridges, not only within discipline, but between disciplines. And so perhaps we can interrogate a single phenomenon with all of these, but we can also look at one of these across a lot of phenomena. I think in chemistry, that's particularly important because we're often asking our students, at least in the higher ed space, to really think about causal mechanistic reasoning, the cause and effect cross-cutting concept across many, many chemical phenomenon. And simultaneously, a curriculum that includes physics, biology, and chemistry simultaneously will often ask students to think about things like stability and change and energy and matter across all of those disciplines, but maybe in nuanced ways. And so I just wanted to sort of point out a little bit about cross-cutting concepts, because certainly more commentary has emerged in the last couple of years about this particular dimension of the framework than was essentially released when the framework came out. And so, as we're likely familiar, the next generation science standards are essentially a unification of these dimensions. And these are operationalized using performance expectations. And I give an example of a performance expectation keyed to matter and its interactions, a high school core idea in the next generation science standards. And I share this particular example just to illustrate the nuanced difference between a performance expectation and what we come to sort of know as a learning objective or a learning goal or something like that for a course. This particular performance expectation is multidimensional. It is having students leverage a particular practice in order to demonstrate their knowledge of a particular core idea. And a learning objective might be, well, just use bonds broken minus bonds formed to calculate an enthalpy difference, okay? And so a student can certainly do that latter thing, but you would never uncover what they think about energy or the release and absorption of energy of chemical reactions simply by calculating an enthalpy change using a formula. And so I just cite this as an example of how these types of performance expectations and leveraging these three dimensions can really begin to unlock a lot more about student understanding of chemistry, rather than some of the things that I know, at least I am guilty of in higher education, of having students do. And so with that, I argue, as many do, that there's really no reason why the K-12 science education framework can't be applied to higher chemistry education. The framework in and of itself is built off of very sound research about student teaching and learning, and leverages cross-cutting concepts and practices that chemical professionals use. And so there's really no reason why we can't fold these things into the undergraduate chemistry space. And Melanie Cooper makes that argument, or made that argument, about 7 years ago in a wonderful editorial in J. Chemed that I cite at the bottom. And if you aren't used to hearing her name, you'll be hearing her name a lot in my talk, because she was really one of the first to grab onto this idea and run with it in the higher chemistry education space.
I have known her for 40 years almost. She has been doing this when nobody else was doing it.
Yeah, exactly.
When she was at Furman, I think. Yeah.
So with that, this afternoon, I wanted to sort of talk about three areas that I feel have been influenced in undergraduate chemistry education by the framework, and that would be curriculum design, assessment, and learning activities. Now, this is going to take a little bit of a different flavor than talking about the framework and the NGSS in the K through 12 space, because, well, the NGSS are the standards by which K through 12 education is extracted in many ways. Higher education does not have a NGSS. We do not have standards, and I don't think we should have standards. That's a conversation for another day. And so I'll really be sharing how the ideas of the framework itself is really influencing these ideas or these areas in higher chem education, and not really talking about how the standards themselves have any impact, because honestly, I don't really think they do, except to give examples of how we should be phrasing learning ideas with regard to what students should be able to do. And so because these things are all intertwined, just please forgive me as I sort of, I jump around and talk about them, because it's hard to talk about one without talking about all three of them. And so I do have two major goals by sharing this with you. I always want to add insight into the question that K through 12 educators often ask me, which is, what do my students need to know to succeed in college or university chemistry? And I hope that by sharing what I think a timeline of the future is for college university chemistry and how it actually can be more well aligned with K through 12 education, I provide some insight into that question. And then I also wanted to introduce college and university chemistry instructors to resources for instructional design and assessment that you might not be familiar with, but you all might be. And so hopefully I'll just be reiterating a point here this afternoon. All right, so we'll start with curriculum design. And curriculum design, when employing the ideas of the framework, really tends to focus on disciplinary core ideas. As I said at the outset, I think one of the major points to a disciplinary core idea is it moves students from having a very fragmented novice type of knowledge structure to a more organized, operationalized knowledge structure that mirrors how experts think about their disciplines. And so with regard to that, if we think about how, for example, general chemistry is structured or has been structured since its inception in, I think, the 1950s and 1960s, we get things like this. And this is not meant to say anything about Navaldo Tro's book. This is reticent of practically every general chemistry textbook out there, that we go chapter by chapter and introduce students to a lot of different topics that by virtue of the design of linear curricula that are in textbooks, we give students a piece by piece or very fragmented type of knowledge structure. And so upon reflecting on that, Melanie Cooper, again, in 2010, reflects on the idea that general chemistry uses a course or curricular design structure that's very inconsistent with the realities and the research about how students learn. If we're wanting to leverage education to help students organize their knowledge structures with regard to chemistry, presenting a litany of disconnected topics is probably doing students no favors. And then quite serendipitously, across the pond, over in Scotland, Alex Johnstone was saying some very similar things when he, this is from some award address, I actually can't remember, but he reflected that there's actually an immediate need for a total reexamination of what is taught, and this probably requires a complete reordering of what is taught. And so we've all been marinating in these commentaries for a decade, and that's sort of the genesis of starting to apply the idea of disciplinary core ideas to reorganizing and designing general chemistry and other courses in the higher ed space. And so when we go from that fragmented approach that I think is typified by our typical general chemistry structures, we then have to adopt disciplinary core ideas to build our curricula around. And this is just one example of that, and one that I'll come back to. But in my work here at UW-Madison, as we think about curricular redesign and things like that, these are two core ideas that we've been playing around with for a one-semester general chemistry class. The idea that structure of matter governs properties and reactivity, and that energies that are implicit at the nanoscale amongst atoms and molecules give rise to macroscopic energies and thus macroscopic properties. I'm not arguing here that these are the core ideas of chemistry. I'm arguing that these are core ideas that are very useful for our particular curricular goals for this particular course at my university. And I think that's the argument that we sort of all make when operationalizing disciplinary core ideas in this context. And so the goal here then is to build curricula that support students making connections amongst seemingly disparate pieces of knowledge, or seemingly disparate when they are presented in ways that are disconnected. And I just want to mention that I'm trying not to typify general chemistry instruction as being solely what a table of contents might give us. I realize that there are many, many instructors who are very gifted at helping students make these connections. But when we sort of look at the general chemistry landscape, I think that's the exception and not necessarily the norm. And so when we sort of are grappling with the idea of a disciplinary core idea versus a topic, some things that we go through here in our curriculum development process are to align those typical topics with our core ideas, to see where things need to stay together and see where things need to be broken up. And I make the argument that that topics in large might be better understood if they are instead situated in core idea groupings rather than in the groupings of topics that we have come to know / maybe love. Definitely know. And here's an example of that. I think a topic in general chemistry that's pretty prevalent in general chemistry is the idea of phases and phase changes. That comes somewhere in thermodynamics, right? And we have, it just sort of is situated there in a typical content progression. But if we break that out into how the core ideas of structure and properties and energy align with that, a little bit of a different picture emerges about how all of this might go together. And again, I'm using the core ideas we have here at UW-Madison. This could be done in other ways. But if we think about the structure and properties portion of phases and phase changes, we get that really wonderful chemistry-centric, very important idea that the melting and boiling point of a substance depends on its structure and the types and strengths of interparticle interactions that are afforded by that structure. And in a typical Gen Chem sequence, that comes well before we get to talking about phase change temperatures, all right? It's sort of done in Lewis structure land, where we make students draw a Lewis structure and predict the forces that might be afforded by that, and it's sort of left alone there, and we go on to other things, right, before we get back to this idea of phase and phase changes. And then the energies associated with those phase changes are determined by those types and strengths of interparticle interactions. And the temperatures then are the result of energy transfers between the system and surroundings and corresponding entropy changes. And so this wonderful core idea-centric story emerges that actually aligns a couple of disparate topics in general chemistry in more of a coherent story than we typically find it. And that's sort of my point here, that once we reimagine general chemistry in a core idea-centric way, we're helping students make connections that are better, that we typically leave them to their own devices to do over a 1 semester or a 2 semester sequence. And so with that introduction to sort of why we're doing and what we're doing, a curriculum known as Chemistry, Life, the Universe and Everything emerged as one of the first core idea-centered curricula in the higher ed space. And this is Melanie Cooper's curriculum that's been operationalized at Michigan State University. They actually centered this around 4 ideas, disciplinary core ideas, electrostatic and bonding interactions, atomic molecular structure and properties, change in stability in chemical systems, and energy. This is a 2-semester type of sequence. And what's wonderful about this curriculum is if you go to clue.chemistry.msu.edu, you can get all of their curricular materials. And so they're very forthcoming about what they've been doing and why they've been doing it. And so it's also worthy of note that just recently they have expanded on their work in the general chemistry space to come up with O-Clue, or maybe depending how you read that representation, benzene clue, which is the organic chemistry curriculum that actually still leverages these particular 4 core ideas just in the organic chemistry topic space. And so aside from the work that we're doing right now, Melanie and her team at Michigan State were really the forerunners with regard to getting this core idea centered curriculum off the ground. And if you take a look at their curricular materials, you'll see some very familiar things with regard to general chemistry, and then you'll see some very, very different things that they've put together. And one of the strengths, I think, of their program is that it has been consistently undergirded by research into student reasoning and learning that I'll get into a little bit later. Another general chemistry curriculum that has emerged as core idea centered is actually chemical thinking. And this has come out of John Pollard and Vicente Dalenker at the University of Arizona. Now, they don't organize their chemistry curriculum by core ideas as Melanie has operationalized them, but they centered their curriculum around questions that guide the chemical enterprise. And I think this does a very, very similar cognitive, it achieves a similar cognitive goal in the flavor of disciplinary core ideas, in that it organizes students' thinking, not necessarily around ideas, but around central questions that chemistry tries to answer. And so over the course of a year, their curriculum, chemical thinking, goes over how do we distinguish substances, how do we determine structure, how do we predict properties, how do we characterize chemical processes, and so on and so forth. Now, is there definitive research that these questions accomplish the same thing as core ideas? No. Still in the spirit of it, that they came up with a general chemistry structure that centers around ways of thinking. Very, very similar to disciplinary core ideas from the framework. And then even more of a large-scale project, Emory University just got through not a general chemistry transformation, but a 4-year chemistry curriculum transformation that was centered around core ideas. They adopted the same core ideas as was present in the CLUE curriculum at Michigan State, but they threaded them through 5 foundational courses. It's what they call foundational, not necessarily what the ACS Committee on Professional Training calls foundational. But I show you here a map of how they thread the core idea of atomic molecular structure and properties throughout the 5 foundational courses. And they've actually gotten rid of the typical names we see in the higher ed space, like general and organic chemistry. They have courses called structure and properties, principles of reactivity, advanced reactivity, macromolecules, and light and matter, that thread through a 2-year sequence the core ideas, and this is just an example of one of them. And so this Emory University curriculum is called Chemistry Unbound, which I think is a very creative name for what they're doing. But I wanted to give an example of how the idea of core ideas is getting out of just coarse-grained size spaces and are being used by departments, at least one department, to look at their entire chemistry curriculum. And then just to highlight back to what we're doing here at the University of Wisconsin-Madison, we decided that for a 1-semester course, it's advanced general chemistry, and for this course, we essentially assume that students have 2 years of high school chemistry, which may or may not be advanced placement as well, that we could center a curriculum around 2 core ideas. And I show you those here again. I won't talk about this in depth, but we're really thinking about how these 2 core ideas are intertwined throughout the entire semester. And we're sort of taking it in 2 phases. Part 1 about structure and property, and part 2 about stability and change. We're ready actually to operationalize part 1 this fall, and then we're going to continue our development work for part 2. But I will say, just personal empiricism, that it was really interesting to work with my colleagues about how to build a curriculum around these 2 core ideas, and how immediately, when we are freeing faculty from the typical general chemistry course textbook contents, that they come up with some very creative things. You might notice that down there in part 2, that kinetics is last in the entire curriculum, where typically in general chemistry it's in the middle and electrochemistry is last. But as we map these core ideas in and consider them with regard to the goals we have for this particular course historically, everything sort of leads to a discussion of kinetics as a final thing in the course, which was a really, really interesting outcome of our work thus far. So please stay tuned. I might have some more to tell you in a couple of years. And if you hear thunder, well, we're being hit by a real big storm outside. So hopefully I don't lose you all. So moving now from curricular development to assessment, and how the framework has really encouraged us to think about a different assessment in a different way. And so the framework sort of implicitly emphasizes assessment as an argument. And this argument claimed that a student does know or does not know something based on evidence elicited by assessment tasks. And for those of you that are familiar with the framework, or for what I'll be presenting here, which is evidence-centered design, I do have to say that because university faculty are sadly never trained in assessment, or really anything with regard to education, these ideas are really, really powerful, because it can really help someone trained as a researcher to think about assessment in a proactive way. And I think this assessment as argument idea is really nicely captured in the NRC report from about 20 years ago, Knowing What Students Know, that every assessment, regardless of its purpose, rests on 3 pillars: a model of how students represent knowledge and develop competence in the subject domain, tasks or situations that allow one to observe students' performance, and an interpretation method for drawing inferences from the performance evidence thus obtained. And this is all essentially captured in work known as evidence-centered design. And here we see that student model, that task model, and that evidence model that was delineated in that quote on the previous slide. We sort of work with these 3 spaces in tandem and iteratively come to an assessment as a result of working with them. We consider what students know and how they should know it, and in what context they should know it, and things like that as the student's model. We consider what evidence would we actually, what evidence we feel would be good evidence for students knowing what they know and in that space of how they know it. And then what things students will be doing to actually elicit that evidence or artifacts or behavior of some sort that build on this model. And so iteratively, we sort of always are thinking about what students should know, what evidence we can elicit from them to be confident that they know those things, and then really think about the tasks that are meant to elicit said evidence. All right. And this is essentially how the NGSS performance expectations were designed. And so we build a student model out of disciplinary core ideas and cross-cutting concepts. That's the what students should know and how they should know it. We build tasks from the practices. And then as we sort of fold all of that into what evidence we would take that students know what we want them to know, we fold that into claim statements, and those are the performance expectations or learning performances that the NGSS is based around. I mention this only because, again, in higher education, we don't have those performance expectations, right? And so it's up to faculty to sort of build those performance expectations or finer grained learning performances to help with their own assessments. And then from those claim statements, we can use those to build these so-called knowledge in use assessments. Students are no longer sort of being assessed on what they know necessarily, but essentially what they can do with what they know is the major paradigm shift here. And so what we have learned so far in the higher education space is that when you actually construct assessments from evidence-centered design, where you can be confident that student reasoning and understanding is actually being probed, you uncover some very surprising things, and maybe, depending on how you look at it, some very depressing things. And the caveat here is that my point is not that students can't do these things. This is not a deficit model that I am expounding here. I'm trying to expound that our curricula fail students a lot of times in what we hope that they can do, all right? So what I'm about to present may look like students can't do this, but my overall point is that they can. We just need curricula to support them in getting there, all right? And so again, work by Melanie Cooper, no surprise, has been sort of the first to develop assessments of student reasoning and understanding that get at our disciplinary core ideas or students' reasoning with them. And back about 5 years ago, that team constructed what is known as the intermolecular forces assessment, which I show you here in the left-hand box. Now, I want to call your attention to items 7 through 9, where they're asking students to draw and label representations that indicates where hydrogen bonding could be present for an ensemble of 3 ethanol molecules, and then describe things that they're not able to actually articulate representationally. And then similarly, do the same for dipole-dipole and London dispersion forces. And so instead of asking questions about what molecule can have a hydrogen bond or something like that, right, they are asking students to actually, okay, give us a representation of what you think this looks like. And what the team did was essentially code student responses. And so on the left-hand side, or that axis, are the intermolecular forces type, hydrogen bonding, dipole-dipole interactions, and London dispersion forces. And then the x-axis here are the 3 different codes that they applied. And what they found basically is that either students represented these intermolecular forces as actually being within a molecule, which we know is scientifically inaccurate, between molecules, which is more what we want them to do, and then something very ambiguous that is like, I have no idea what the student is actually trying to tell me. And they binned their responses thusly. And I'll give everyone a minute to sort of take that all in. I think that up there in hydrogen bonding within the molecule, something we may all have seen at one time or another, that they are circling. Well, we teach our students that hydrogen bonding has something to do with a hydrogen being attached to a very electronegative atom, like an oxygen. And they are certainly circling a hydrogen that's associated with an electronegative oxygen, but are missing a bigger part of the picture here. And so pay attention to the idea that students are in many ways representing intermolecular interactions as between molecules, or actually within the molecule. They're just circling covalent bonds, or who knows what they might be circling for a London dispersion force. But an overarching point of other than just documenting all of that is that these issues were characterized not just by low achieving students. And so they were able to look at students' final exam scores or ACS exam scores or different things like that, and found that students who got A's in the course were just as likely to show those ineffectual or inaccurate representations, just as someone who got a D was. Someone who got in the 95th percentile of that ACS exam were just as likely to show those inaccurate representations as were students in the 15th percentile. I'm probably quoting the paper inaccurately, but I think you get my point. As well as the fact that these misunderstandings seem to be agnostic of active learning environments as well. And so here what I show you is a percentage of students that are giving these types of codes, at least the within and between codes, in various types of courses. And so on the left there are the within codes for the 3 different intermolecular interactions. And then on the right are the between codes. And so this is a variety of courses, traditional being in this paper, the non-CLUE curriculum. And then the CLUE being the CLUE curriculum that Melanie and her colleagues have been espousing. And we can see that in the traditional curricula, we see that the within codes are being represented far more than the between codes in the red bars. And these were courses that were doing everything that we need to be doing in our classrooms, right? The students are talking to each other, they're answering clicker questions, they're being very active. But we still have these issues that, regardless of that, students don't know what a hydrogen bond is. Versus what the CLUE curriculum is doing, and really leveraging core ideas, really leveraging practice-based assessments, and we're seeing that students are getting are displaying those more accurate representations. And so this is but one example of how this team at Michigan State has really hammered home the idea that the way that the content of a course is structured and the ways it's assessed are at least as important as the pedagogy that we're deploying within the classroom. They're showing very nicely that you can be as active as you would like in the classroom, but unless the curriculum and the assessment is aligned to leverage student reasoning and understanding of core ideas, we're going to get students who are drawing hydrogen bonds as an oxygen-hydrogen covalent bond, and still getting 100% on assessments that are not aligned to pick up those differences. And so thankfully, that team is also creating tools that are helping faculty design assessments that have a greater potential to elicit evidence of student understanding. This came out about 4 years ago. It's called the 3D Lab. And what the 3D Lab gives you is essentially a way to interrogate your assessments to see where the core idea is, where the practice is, where the cross-cutting concept is. And all of that leverages these evidence-centered design perspectives to give instructors more confidence that their assessment items are actually have the potential to elicit evidence of student reasoning. And there's also guidelines to help students or instructors, excuse me, adapt what they've already done to be more aligned with that framework. And I'm happy to report also that the American Chemical Society has gotten involved with this. Anytime we do, for example, new faculty workshops, and you get someone like me doing the assessment part of that, we are really teaching new faculty these ideas of assessment as argument when we're thinking about measuring learning. We are giving new faculty practice at deconstructing assessment items and figuring out whether they align to the practice of constructing explanations or not. And so we've been doing this for about 3 years now, with not the workshops themselves, but really impressing upon new faculty these ideas. I know I'm running out of time, so I will skip to the idea that we're also really getting at classroom practice as well, because, well, if you design a curriculum and then you try to assess that curriculum without actually doing anything relevant in the classroom, you're going to fail in that connection. So we need to bring in the other side of this triangle. And that's another set of initiatives that the American Chemical Society is taking on with regard to developing classroom activities and things like that that are aligned to the framework. We've put on 2 workshops so far. We've trained faculty from about 31 institutions in a methodology that's actually quite the inverse of K-12 professional development. There you all start with the performance expectations and work down to classroom types of activities. And here we have to start, because we don't have performance expectations, we have to generate our own learning performances and then unpack those activities. And from that work, we've actually been working more closely with a set of 4 institutions. We've come up with ways to help faculty in the higher ed space actually communicate with one another with regard to the activities that they are designing. And so we've come up with a consensus learning activity structure that we use to help, again, faculty communicate from institution to institution. And we have a litany of great examples that faculty are developing in their own courses. This is from Sam Houston University and Adrian Vialta Cerdes, who developed some really great work around chemical kinetics and leveraging collision theory as a model to help students understand how, for example, changing solvent impacts the kinetics of a reaction. So in summary here, I hope I've given everyone listening some insight into how the framework is influencing higher chemistry education. Curriculum design is really looking at core ideas. And again, we don't necessarily believe that there's one set of core ideas that can be operationalized for all of chemistry. This is really coming down to the institutional context and goals of particular classes. But nonetheless, we believe the core idea-based curriculum structures will help students be able to connect disparate ideas and end up with structures that are considerably different from the traditional canons that are out there. In the assessment space, the idea of evidence-centered design and using assessment as argument are being employed to help assess student reasoning and understanding. And when you do that, you really see some surprising things. And I'm happy to say that when faculty do see those surprising things, that really does galvanize their want to change their assessment practices and their classroom practices to help students get to where we want them to get. And I skipped over this argument a little bit, but as far as learning activities and practices, these ideas of being active or inquiry or critical thinking, these words, right, that when we ask teachers and faculty what they mean, we get 100 different answers. We really are coalescing around the more tangible scientific practices as ways that we operationalize these idiosyncratic terms that have multiple meanings depending on what you talk about. And we can talk about that a little bit more in the discussion period here. But I'm happy to say that coalescing around the scientific practices really does galvanize all of these words and inherently engages students in all of these practices, no matter how you define them or not. And lastly, this isn't just a work that's being done in isolated pockets around the country. Our governing body, the American Chemical Society, is consistently supporting faculty professional development initiatives that engage faculty with these ideas. So with that, thank you so much for joining me in this very Zoomy world. And I am happy to answer questions, or I'm happy to be part of a greater discussion amongst all of y'all to look at this further. So thanks very much.
Thank you. Thank you, Sam.
I have a question.
Yeah, I made
Go ahead,
it. Go ahead.
Okay. Hi, Sam. Thank you. My question has 3 parts, but they all center around the word laboratory.
Gotcha. Go for it.
So what does lab experimentation look like in higher ed now, let's say in a 4-year university or college? And what's the latest research on the role of lab in chem education or success in, when I say the role of it, I mean, in success in chemical education, so that your freshmen don't drop out of chemistry entirely? And how's lab assessed?
Great question. So here we go. Lab in higher ed is anywhere on a continuum from really well thought out, authentic types of experiences, all the way back down to cookie cutter, carry out this procedure and come up with an answer that we've known for 100 years.
Okay.
And I wish I could say that that was 50-50, but it's certainly not. I think it's far more the latter than it is the former.
I noticed on one of your publications, you co-authored with John Wink.
Yeah, yeah.
And, oh, it has to be maybe 8 or 9 years ago that I was at a summer program with him in Chicago. Mm-hmm. His labs were really authentic labs.
Yeah.
But boy, I don't see how everyone can conduct those labs. He had training, and he even had training of the people who assisted him, his lab assistants, his grad students, et cetera, to really be able to address the students, because you have a student coming into a truly what you call, and without going into it all, I know what you mean by a truly authentic experiment. It's tough.
Absolutely tough. And certainly different universities have different resources, personnel, money to sort of accomplish all of this, right? But you know, that said, to the first of your tripartite question, I think the name of the game is still, here's a lab manual, do this experiment, do this activity. I can't even call it an experiment. And we're going to verify your answer. And the goal of students is to just get out, right? They have no learning goals. That was really well articulated a number of years ago by a big study that Marcy Towns at Purdue University did, that the number one learning goal of students with lab was not a learning goal at all. It was just to do it and get out. Mm-hmm. And so that's the first part of your question. Now, the role of lab, I think, is directly related to what we see in what the lab actually is. Programs that truly believe the role of the lab is to have authentic experience of a scientist, of a chemist, to develop skills. You see labs being changed to authentic experiments. You see labs being changed to badging type structures, which really focus on the development of skills and students performing those skills and different things like that, versus, well, programs that probably never put much thought into what this lab is supposed to be, but it's historically there. And that's all we've ever really given credit to. Or the American Chemical Society Committee on Professional Training says that my students have to have 400 hours of lab. And so we're going to give them 400 hours of lab without any other thought to that. But I think to your last point, is the really, really important one. How is lab assessed, and what does research show about it all? And the fact that a lot of labs have no purpose makes them inaccessible with regard to student learning, right? Because if you don't have any learning goals for your lab, if you're just sending students in and they are doing this book, what is there to assess, right? So inherently, a lot of curricula have labs that are inaccessible because they're not built on anything that you can assess, right? And that's a real problem. It makes this question really, really hard to ask because it's a chicken and egg problem. Mm-hmm. And only in programs that we have authentic experiences or programs in which skill development is really put forward, do we see assessment structures, well, that say very simply, well, if you are prizing the development of skills and you assess the development of skills, the students are gaining those skills. Cool. That's not brain surgery, but it is completely state of the art as far as lab education is concerned. If you assess students with regard to inauthentic experiences about the nature of science and things like that, they have a better understanding of the nature of science. Hooray, right? And so it is the exact answers you might expect, but they're happening in such isolated pockets that all of this is not being sort of taken up by the broader community yet.
Okay, yeah.
So I see that another hand is being raised. Did I sort of get at your question?
Yes, sadly, yes.
Yeah.
Well,
And
Sam, sorry. What I do is I do freshman labs,
yeah,
and I hate to think that everything we're doing is, I don't know, what shall I say, all for naught. When you say building skills, my philosophy with the beginning of lab as a freshman, the first semester, is to build a series of skills so that they know how to use lab equipment properly and how to take data and make some kind of conclusions from it, how to massage it, what tools to use to do that with.
great.
Is that not meaningful?
Oh, absolutely. And I apologize for, in trying to answer a question characterizing what is a really huge continuum with regard to how people are doing this. And so absolutely, anytime you can engage students in authentic practices, right? An argument for evidence, modeling data and different things like that, that is fantastic. I still see it though as not the norm, but the exception.
Well, that's hard to believe. I mean, I would think that an authentic lab would be more a lab that deals with a question for which, I mean, we're always using like Beer's Law Lab. I mean, there's no, give me a break. But to actually see it in action and to touch it and feel it and do some of the things brings that to a better understanding of what that means. You can talk about it, but when you do it, it's a different story, I hope. But anyway, so, but I would think that a more authentic lab program would have things that you are developing that don't have a specific endpoint answer all the time, and that you're actually constructing knowledge about something that you may not even know a whole lot about. Is that correct? That's what I would assume, but that's very difficult.
Yeah, no, that would be more to what I call authentic. And,
Yes.
and sure, there can be, there can be scaffolding of that authenticity.
Yes,
There can
yes,
certainly be
of course.
corrections, right? Because, well, if you're going to do an experiment, a real experiment that has a UV vis spectrometer, there better be ways to teach students how to use that UV vis spectrometer.
That's right.
Or else it's going to break and you're going to be out a lot of money. And so yeah, to your point, those are difficult, but the fact of the matter is that even the non-difficult ways still cost a lot of money with teaching assistants, with lab equipment and all of this stuff. And until we get into a mind frame of collecting evidence that this is actually working, it's going to be really hard to justify those expenditures, especially because we've just spent a summer creating online experiences for labs, which a non-scientist administrator might go, well, then why have we been doing this in the lab for 100 years?
That's a fear for many of us, I think. It's going to come to that. Yeah. Come back to that question of authentic labs. I think some of us organic chemists have been trying to do it. I think the forerunner of that from a lab manual perspective was Lehman. I forgot the name of the book. John Lehman's lab manual was, I think, inquiry-based labs. And then Jerry Morick at Carleton, I think he's another one who again was a proponent of that, and with the help of NSF, many of us were trained in that. I mean, I abandoned the cookbook experiments 20 years ago almost. 2004 is when I switched to this inquiry-based lab. So no more verifying the melting point of acetanilide or whatever that you and I probably did. Maybe not you, I did. That was my first organic chemistry experiment. Recrystallize and take the melting point of acetanilide. So, yeah, I mean, I learned how to recrystallize, how to do melting points, but nothing much more than that. So
good for you, Mel. And I think you know, considering the conference that we're all at right now, I think this becomes preaching to the choir.
Yeah, I know.
Rather than actually knowing the bigger landscape of things. And so I am not criticizing or talking about you all, right?
No. I have a question. When you talked about the faculty workshops, are they only for the new faculty or maybe those who are in 5, 6 years, 10 years into teaching?
Yeah, sure. So there are actually two kinds of workshops that the ACS has been doing. There have been ones that are just for new faculty.
Yeah, I know one of my colleagues went there. Yeah.
Just one assessment is just one thing. And then these were called at the time the ACS performance expectations workshops, because we were all very naive about that, how that construct actually plays on the landscape of higher ed. These in the future will be called general chemistry in 3 dimensions workshops. And these are open to any faculty teams that want to participate. We are just sitting on pins and needles right now about the NSF grant that we hope to fund the future.
Okay. All right, good. That's good to know. Yeah.
I have another, I don't know if it's a question, observation, but it's, I mean, my background is teaching high school kids, and I feel that's why I have the approach I do about what I do in class, which is, it's very important to me that, you know, like, again, I'm sure we all agree on this, that every kid leaves there with an improved understanding of how things fit together, about their confidence level, about, X, Y, Z, 100,000 things. And sometimes I think that's, you know, it's funny, I may have a different approach than some of the professors, but I think it speaks to the kids. I find some kids, and the other thing is some kids, they come from high school, but they haven't learned any of these things. And it's almost like, I don't know what happened. All the standards, all the kind of training the teachers have gone through, and the kids still have the same expectations of a more rote approach to understanding things. And I don't understand that. How are we going to change their attitudes about what learning really is? How do we do that?
Yeah, I think that we have to send a consistent message from their high school chemistry all the way through their undergraduate, that we are going to demand evidence of their understanding and reasoning.
Okay.
Right? It's not going to be enough to just pick which molecule A through D can have a hydrogen bond. But I'm going to expect you to create a model of molecules, show me a hydrogen bond, and explain to me why that ethanol molecule has a different melting point than a dimethyl ether, for example. And I think that, sadly, I have to say anecdotally, because I don't think there's a research result that points to this particular point. Sorry, but as we keep our demands of students and what they're supposed to do with their knowledge, rather than just the knowledge that they have, they do rise to the occasion. We did see some wonderful, when we started our work here at UW last fall, we were just changing some things here and there to sort of take the temperature. And as soon as we began to demand that students put together this causal mechanistic reasoning of boiling points, they were right there with us. We just needed to do it. We needed to demonstrate it in class, and it needed to be on the assessment. Now, I know that's a very simplistic answer to your question, right? Because we only have so much time here. And I also realize that I'm dealing with an advanced general chemistry class, which is very, very different than other learning environments as well. But I also think that Melanie Cooper's work with CLUE really demonstrates that when you when you just change the curriculum and set the expectations of that students are doing things with their knowledge, they sort of end up doing it. Now, granted, it's a lot harder than that, but that is essentially my short answer to your question, Kathy.
No, I know. I know from experience, as I taught in an alternative school for a lot of my life, that, you know, it takes several years to change a culture of learning. And, you know, I guess everything we do helps change that culture some. And so maybe I'm just seeing the beginning of it. Maybe as they go along, I notice that the kids who are engaged really are engaged, you know. And so maybe we just need a bigger picture of that, you know, rather than the small pieces that we see.
Yeah,
But,
and yeah, to your point, it takes a lot of time, and students are great at learning, but they're great at learning not necessarily what we want them to learn. They're good at gaming the system, and so they
right.
could have moved from Mr. Benigna's amazing high school chemistry class that I know leverages a lot of what I've been talking about today, and then go to someone's general chemistry class and completely reset because
Yeah.
they're gaming what's going to get them an A.
Yes.
Right,
Yes,
and it's going to
yes.
be a different set of standards than Jamie necessarily held them to.
Thank you.
Well, so there's a couple of things on that end, and yes, thank you, Sam, for using my last name, which my students in my former school never actually did. But so there's a couple of things, like there's the modeling curriculum that is very much a reset, if you will, about how do we do processes in high school education that set students up for deep thinking, building their own models, constructivist approaches, stuff like that. Even in College Board, they're developing a pre-AP sequence to try to get more kids ready for AP level coursework in high school, right? So like we've kind of reached the cap of like, all right, we found all the kids who are AP ready in school, and now we need to build the pool bigger to get more kids AP ready before they leave high school. So I think there's a couple of parallel tracks that are running down this road of rote memorization is not your greatest strategy for success anymore. And so, but again, it's a slow steer to get there. And then also, like, a kid could have a wonderful high school experience and then go to a Gen Chem classroom where rote memorization is expected. And so you've got to steer all the ships in a general direction.
And then we're actually hurting those students who had that rich high school experience, right? Because they're experiencing now this cognitive dissonance of what I did before is not what they're expecting here. Right.
And my deep thinking isn't valued.
right, exactly. And
Wow.
well, it is
Wow.
in many cases.
One thing on the lab bit though, like, you know, it's taken how many decades of Gen Chem before we've started to reevaluate what are the effective tools by which we can line up a curriculum such that kids will learn things and have outcomes that are accessible. And that is in a much more intensive assessment space of curriculum in a classroom. And we haven't really done assessment space of laboratory.
Right.
Like there aren't, other than like maybe A-level exams have laboratory practical in the UK, but there isn't really like an assessment of laboratory model in the United States. So it might be a really interesting thing to pursue, like what do we establish as goals of a laboratory program, and then how do we check that students are demonstrating competency there?
Some people are doing some great work on it. From not only sort of an evidence-centered design perspective, but also like, it's amazing that you actually have to develop an assessment to make sure that the scientific practices are being done in a lab. But people have to do that because in these cookie cutter labs, that isn't necessarily happening. And so there are some isolated things. Hopefully that's the next big hurdle, but I can send everyone or just ask you to look up Stacey Lowry Bretz's editorial from about a year ago in JCE, where she essentially outlines that we're in trouble because labs aren't being assessed. We have no data that anything about a lab is working, whatever how you define working as. And then that was followed up by a series of webinars from the ACS when all of this virtual stuff started to happen. when there were sort of the torch carriers of labs can never be virtual, and it's like, well, a virtual lab might be better than some of y'all's actual in-person lab experience. If you concentrate on certain things. And so I am happy to
A well-structured virtual lab. Good do that.
Yeah. I mean, certainly you're not going to learn how to literally have the hand action of a stopcock, right? But you might be processing and analyzing and modeling data very, very well, which is something your in-person lab experience probably never had you do. So calm down, torch carrying chemists.
Thank you, Sam.
Oh man. So
yeah, I think we should go ahead and close this. Thank you, Sam,
Sam.
Thank you.
for presenting. It was quite interesting, of course, and eye-opening for many of us. I wish there were more people, but I think it's all of us are higher ed people at least, so we could appreciate what you said more. Joe, is that your name? What's your
Jamie Benigno.
Jamie. Yeah. You are from AP, I guess.
Yes, I recently switched jobs to work for College Board. So yes,
okay. I mean, I was going to mention that I graded the AP exam this time. I have been doing it, and they only had two big questions. That's it. But that question that I graded was very well done. It measured.
Thank you, Sam.
Thank you, Kath.
It did measure, assess the knowledge pretty well of a whole bunch of ideas. So you
glad to hear it.
What were the two topics?
Oh shoot! The one I was grading was more related to the intermolecular forces. So.
Yeah, so think of it as they were two questions. One was 12 points, one was 8, and across 20 points, we had to measure 7 units of instruction, which were atomic structure, molecular structure, bonding, chemical reactions, spectroscopy, kinetics, thermochemistry, not delta S or delta G, and basics of equilibrium, single phase and multi-phase, but not acid base.
Yeah, but it was. I thought it was well done. At least the one I graded probably 3,000 of them, but it was good. Anyway, thank you, Sam. Yeah, thank you.
My pleasure. Great to see you all.
Thank you.
Take care.
Sam, I will see you later this week, I think, right? 11.
Oh, yeah, Socket B. Good times. ACS volunteering just keeps continuing. Of a national meeting.
Sam, is your PowerPoint in the Google share deck thing?
Not yet, because in grandstand fashion, I finished the presentation 5 minutes before I logged on here. So
yeah, your bibliography just rapidly expanded my reading list. So.
Good to know. But I will coordinate with Mel to make sure the slides get into that Google Drive. Okay.
Okay. Thank you.
Sure thing. Take care, everyone. Good to see you.
Bye.
Good to see you. Nice. See you, Mary, and see you, Jamie. Nice meeting you.
Yeah, see you as well.
Thanks, Mel.
Bye.